All right. Good morning and welcome back. So today we will continue uh, the lecture on backpropagation algorithm. So last time we ended here. Okay, we actually started our analysis from this simple computation graph that has basically two layers of neural networks. Okay, so we started our analysis just like the way we did for logistic regression, which is even uh, which is actually the simplest case of the uh, backward step that we have seen. So uh, everything on the right, we started from the gradients on the right part, which is the gradients for the dA. Okay, so these d, the variable names with d before it as a prefix indicates the gradients. That's the convention that we take for the convenience of writing programs, right? So if you want to program in Python to indicate some variable that this is the gradients for another variable, then we simply put a d before a. Okay, so and this is also in short for a short form or easier form for writing this partial derivative or the derivative of the loss with respect to some uh, parameter or to some variables. That is just too heavy to write such a form, so we use d to indicate that form. All right, so the backwards step means that we need to go from the loss, which is so this y hat is a prediction. So we will start from the loss, and the loss can be computed by some loss function between that computes the deviation from the prediction to the actual label. Okay, and we go backwards by looking at this step, the A2, and we need to compute the gradients of that variable. So this A, you can think of it as a intermediate variable that we use in the computation graph. Okay, so it's essentially it's not different from the intermediate variable like u and v that we used before in the very beginning for introducing the computation graph. For example, the u can be a plus b, and the v can be c times u, and so on. So these u and v are just the intermediate variables. And so the rows of a and z's are exactly like the u and v's because we want to use them to define the computation graph, and so that we can know how the parameters are, so how the parameters can be updated using the backward step. Okay, so we will going back from the loss to the dA and to dz, right? And because the dz, the z is directly computed from the A2, from the A1 and the W and B. So it's and it is a linear combination. So it's easy to derive that the gradients for dB is exactly the form of dz2. Okay, dB2 is exactly the form of dz2. And for dw2, we basically analyze the shape of w2, right? And because z is computed as the dot product between w and the a, so the gradients for w is the same shape of w2. So, and the partial derivative here, the partial derivative of z2 with respect to capital W2 is our focus of analysis, because this is a partial derivative with respect to a matrix although in the case, this matrix has just one row, but in practice, it could be multiple rows, okay? So in this one row case, it's a bit easy because we can easily observe that in order to make the gradients of W to be the same shape as the original W, we need to compute dW2 by dz2 times the transpose of A1. Okay, and A1 is a column vector, right? But if we transpose it, it becomes a row vector. And dz2 in this case is just a one number. So the dot product between dz2 and the row number will result in a row vector. And that row vector is the same dimension as the row in W2. Okay. So similarly, we will compute dA1 and dZ1. Okay. So in the computation of dA1, there's another tricky part is we transpose W2. Okay. So this is also decided by the computation from Z2, from A1 to Z2, okay? And this time we think of A1 as variables and the W's as constants, okay? So in order to make the shape of the A1, or in order to keep the A1 to be the same dimension as A1, we simply need to transpose W2 and then times it with the dz2. Okay. So I'll fast forward to the end of this slide. So in the end of the day, we need to so the nature of the backprop actually concentrates to these formulas that we need to memorize. It's basically the gradients of W and B's that we need to compute, okay? And in this particular case, the gradients for W is the gradients of the next, or the, I would say next, I use the word next to indicate the future layer, okay? The layer that appears at the later part of the network, okay? So I'd call it next. And I use previous layer to indicate the layer that appears in the earlier stage of the network and the earlier part of the network. So the gradients for W can be computed by the dot product between the gradients of the next Z and the transpose of the previous activation A, okay? And that applies to all layers. So in the first layer, the A of the previous layer is exactly the input. Okay, we can think of the input as the initial layer. Okay, so it's eventually we just need to memorize this dot product. Okay, but we'll look at a little bit more complex example in which we have a different set of layer, or a different shape of the output layer. So in this case, our output layer has two variables, okay? Has two neurons or two units instead of one, because in a one unit layer, it's no different than a logistic regression. Okay, so in order to have a better idea of how the backprop algorithm computes the gradients, we'll look at a slightly more complex example here. Okay, so okay, on this slide, I highlighted these the parameters that connects the input to the first layer. Okay, but this part we have already done. Because it's basically the same example as the previous slide, okay? Or probably we haven't done so. Okay, so anyway, let's go through this quickly. So if we focus on the connection from the input to the first hidden layer, or let's just call it the first layer. We know that the shape of W1, the capital W1 is a 4x3 matrix. It has 4 units, okay, and it has 3 columns that connects the 3 inputs units. Okay, so that's how we compute the z. Okay, and we want to know the partial derivative of z1. Okay, z1 itself is a vector. We want to know the partial derivative of a vector with respect to a matrix W. Okay, so what we need to do is that we take each component or take each unit in Z, and because that is a number now, and we take the derivative of that number with respect to each entry in the matrix, in the W matrix, respectively. Okay, so that is the way we need to do for computing the partial derivative of a vector with respect to a matrix. Okay, and we know this vector has 4 components. Okay, right? So that's why we need to lay this matrix into this quantity into a column vector as well. Okay, but we soon realize that there's only one element left, which is x1. Okay, and the partial derivative, or there's only one element left, which is the partial derivative of the first unit in Z1 with respect to W11. And the value or the result of this computation is x1. Okay, so anyway, we compute this, we conduct this computation on each possible combinations. Okay, and we will have the partial derivatives with respect to the first row and the second row of W, the third row and the fourth row. Okay, so we can now combine these rows back into a compact example. Okay, so in the result part here, all the z's, the z is not a number now, the z is a vector now, and the W is also a matrix now. We can write this seemingly complex quantity, which we didn't know how to compute at the beginning, but now we found that it is a pretty neat form. It's just a 4x3 column matrix, okay, which is the same shape as the W itself, okay, and all these values are the partial derivatives that we need to keep, okay. So remember that this is not the end of our computation. The goal is this quantity, okay. Now we need to connect this quantity with the dz, okay, because dz is from the next layer. The next layer tells the current layer that dz is this one, and then we will use the partial derivative we just computed to connect it with dz in order to compute dw. Okay, so we need to use dz1 to times the partial derivative, and now we need to consider the shapes, because dz1 is a 4x1 vector, right? and the partial derivative is a 4 by 3. Okay, so this partial derivative is 4 by 3, and this dz is a 4 by 1 vector. So how do we come up with a result that has the same shape as dw? We need to put dz1 as a column vector on the left, and transpose x and put it on the right. Okay, so that we compute the outer product between dz1 and the x, or we can say it's a dot product or inner product between dz1 and the x transpose. Okay, so that is how we get dw1. Okay, I think we have been through this last time. So then the next slide, we're gonna look at the more complex setting for the output layer, right? So the difference we have here is that the output layer has 2 neurons or 2 units, right? And we'll look at how we compute the gradients for dw2. Okay, so now we'll do a comparison, because previously the output layer only has 1 unit, and we know the z is a number because it's just 1 neuron. It is the dot product between the w2. So the w2 is in lowercase because if the output has just 1 neuron, then the weight parameter is just a 1 row vector. Okay, so that's the previous results, and it's easy to know that the partial derivative of z2 with respect to w2, and the w2 is a row vector, so it's easy to know that this partial derivative is also a row vector, which is the a1 transposed. Okay, so now we now has 2 nodes. That means our w's has 2 rows instead of 1 rows, right? So that is the forward pass. So this computation is the forward pass, right? It's the inner product or the matrix multiplication between this W matrix and the input from the previous, which is A1. Okay, so that means the partial derivative of the Z2 with respect to W2 also has 2 rows. Okay, and each row, it has the same value, which is A1 transposed. Okay, and that means the gradients of W2 is the same form as the case that W only has 1 row. So already, although W2 has 2 rows now, but since each row, the partial derivatives has 2 rows and each row has the same value. So we can simply use A1 transpose times dz2 times A1 transpose to compute the gradients for dw2. So it's the same form of solution for dw2. Okay, so this is a bit complex example, but we show that the rule or the principle of times dz2 with A1 transpose still applies. Okay, no matter how many rows the parameters have. Okay, so we can generally conclude by that if we want to compute the gradients of a weight matrix, we need to use 2 parts. First is the z of the next layer, okay, and or we say current layer because the w belongs to layer L2. Okay, so let's say we take the gradients of z, dz of the current layer, and times it with the activation of the previous layer but transposed. That is the general principle we need to apply in order to compute the gradients. Okay. So let's look at another computation, because we are done with DW, right? We now another important step in this backprop process is the computation of dA of the previous layer. Ryan asked, can we compute the same? Can do the same calculation for all values regardless of the amount of layers. If by the number of layers you mean how many layers you have for one neural network, yes, that's correct, because the analysis or the backprop step that we analyze here is just between two layers. Okay, we can apply this calculation to multiple layers, and we can stack as many layers as possible. Okay, although there will be practical issues when you have too many layers. Okay, because basically speaking, the gradients for the parameters is a product. It's the product between numbers. So if you do this product too many times, we know that if you calculate the product for between too many numbers, that result can be too large or too small, right? So that is the so-called gradients vanishing or vanishing gradients issue we will deal with in order to make a very deep neural network really practical for use, really trainable. Okay, so if we have gradients that are too large, then our parameters get updated to with too much a step. Within each gradient descent, the step will be too big, so the parameters will not be updated efficiently or effectively. Or if the gradients are too small, then the learning is also slow, which we want to prevent as well. Sorry, I misclicked on my slide, so let me share the screen again. Okay, so now we're gonna look at the analysis or the computation for dA more closely. Okay, so dA, to computing the gradients of dA of the previous layer from the current layer, this is the back propagation step where the propagation happens. Okay, because we want to propagate the gradients of the current layer to the previous layer so that the previous layer know how to update their parameters, right? We don't want the gradients to stay in the current layer. So previously we updated DW, but the DW here, the DW here is at layer L. That is still the quantity of this layer. Okay, so we want to know how we need to update AL minus 1. So that's the next step we will go through. Okay, we want to know, so in this example, we want to know the dA of layer 1 from DZ2. Okay, but in general, we want to know the dA of previous layer given the current layer. Okay, so we know the computation between the connection between Z2 and A1 is a simple linear combination. So previously, when the output layer only has one node, so we already shown this in the previous slide, right? So this is the same. So, but the difference is that now we treat these A's as the target variables. Okay. So the partial derivatives between Z and A1 is W2 transposed. And in this case, it's a column vector because W2 only has one row. Okay, so that's the results for when the output only has one node. Okay, if we apply the rules of computing the gradients, we know that the gradients of dA1 is W2 transposed times dZ2. Okay, that's something we know. But now the output has two units. So we'll look at if it's still the same case here. Okay, so what we need to compute is dZ2, the partial derivative of Z2 with respect to A1. And in this case, both Z2 here, the quantity, the variable in the numerator, and A1, they are all vectors. Okay, so it's the similar case as the partial derivative with respect to W. So, but it's easier because A1 is a vector and Z2 is also a vector. They are not matrices. So all we need to do is to take the partial derivative of each component in Z2 with respect to each component in A1. Okay, so if we look at them closely, we know that the partial derivative of Z1 with respect to A1 exactly A11, and Z1 with respect to A2 is a W12. So anyway, we would have a 2×4 shape matrix, which is exactly W2 itself. Okay, that is something we know. And we know that the partial derivatives with respect to A1 exist in the first column, right? And the partial derivative with respect to A2 exists in the second column, and so on in the third and the fourth. Okay, so we can infer from this shape of the partial derivatives that the gradients is the transpose of these partial derivatives times dz2. Okay, because dz2 is a column vector that has two elements, and in order to multiply a 2×4 matrix with a 2×1 vector, we need to transpose that W, okay, matrix, and so that the resulting dA1 is a 4×1 vector, which is the same shape as A1. Okay. All right. So we've shown that regardless of how many layers we have for the outputs, regardless it's one node or two node, we have the same form of solution for the dAs, right? dAs is just the parameter is the weight matrix transposed times the dz from the next node. That is how the propagation happens, or the propagation occurs from dz2 to dA1. Okay, so that's basically all we need to know about the backprop algorithm. Okay, but if we want to know better how the meaning, what the meanings are, like why we need to, why at the end we need to transpose W2 and why we need to transpose dA2, we can rely on the next few slides. Okay. Sorry, I need to leave for a minute. I hear someone knocking the door. Okay. Could you take a break for 1 minute or so? I will pause the recording here. Okay, I'm back. So in this slide, I summarized the general principles. So no matter whether it's first hidden layer, second hidden layer, or the output layer, if you look at the layer L, okay, and we call so if we look at the connection between layer L and the L+1, so The forward pass computation is described by the formula like z equals w times a plus b, right? And also we must know the dimensions for these parameters. The w has that many rows, which is the same number of neurons or number of units in the current layer, and L is the number of units in the previous layer. So given this information, we can easily verify that the gradients for the current W is the gradients of current Z times the A transpose, the A of previous layer transposed, because we can simply check the dimensions, right? Because the D of W needs to be the same dimension as W itself, okay? We know the W is NL plus 1 times NL, and the DZL plus 1 is also NL plus 1 by 1. And the AL transposed is 1 by NL. So we are multiply these two vectors together, and the 1 will be gone, will be limited according to the principle or the rule of matrix multiplication. Okay, so the result is L plus 1 by NL, which is exactly what we need. Okay, we can also use this to examine the quantities examine the dimensions for DA. Okay, so the DA of the previous layer is WL plus 1 transposed times DZ of DZL plus 1. And the AL is NL by 1, and the WL plus 1 transposed is NL by NL plus 1. And if we times it with a DZ L plus 1, then the dimensions here are gone, and the resulting vector is a NL by 1 vector. Okay, so this principle is easy to remember and easy to verify, because when you don't remember the form, you simply try to match the dimensions. That's how exactly you can memorize them. Okay, so if you don't remember whether W should be to the left or to the right, you should check the dimensions of W, and so that the result is what you need. Okay, and here we have one more step, because we have the AL computed, and we eventually want to know DZL, right? And the connection between Z and A at the same layer, okay, is the activation function. So we need to apply the derivatives of the activation functions using a element-wise multiplication, okay? And if we substitute this one into the equation, it will be like this. So this element-wise multiplication is something different from a dot product, because here the connection between Z and A in the same layer, it occurs to each element individually. Okay, so that's the general principles for computing the derivatives from the next layer to the previous layer. Okay, and then we can pass on the DZL to the even further to layers that are even further behind. Okay. All right. So now there are two slides. I think that will be helpful for you to understand the nature of backprop algorithm, why we need to transpose the vectors, why we need to transpose the A's. Okay. So the nature of a neural network is a computation graph. Okay, if we stand from the perspective of a computation graph, then when we look at how gradients flow backward, we need to look at how many connections from the current units exist to the previous layers. So in this example here, from the hidden layer that has 4 units to the current layer, or let's say from the current layer that has 3 units, it connects to the previous layer that has 4 units. Okay, so if we only look at the gradients of DZ1, which is the first units of the next layer, then the computation of Z1 in the forward pass, it relies on all the 4 units, all the 4 activations from the previous layer, right? It's the dot product between the matrix, the weight matrix, and the activations. Okay, so that's why we have 4 arrows back, because there are 4 arrows, there are 4 black arrows in the forward step. So we need 4 red arrows backward, okay, in order to make the computation graph complete. Okay, so along the path of each red arrow, we need to compute the gradients for each parameters. And we know that each arrow or each path indicates each entry in the first row of the W matrix. Okay, so we need to compute DW11, 12, 13, and 14. Okay, and that is exactly why we need to transpose A1, because so that after A1 transpose, it's the same shape as the first row of W. Okay, so again, now if we look at the gradients of A1 in the previous layer, okay, because A1, the activation of A1 is used in the computation of Z1, Z2, and Z3. It is involved in the computation of all the 3 units in the second layer or in the next layer. So that's why we will have 3 forward pass or 3 backward pass in the backward step. Okay, so we basically need to look at the first columns of W. Okay, and the computation of the quantity of dA1 is contributed by all 3 DZs, because we have one DZ1, DZ2, and DZ3. So all of these 3 units in the second layer contributes to the gradients of dA1. Okay, so the path along these 3 connections, they need to be considered when we compute the gradients for dA. Okay, and they are exactly the results after we transpose W. Okay, so in practice, we need to transpose W2 in order to compute the gradients of dA. So I hope these 2 figures help you understand the need of transposing A1 when we compute the gradients of W, and the transposing the need of transposing W when we compute the gradients of A. Okay, so let's wrap up a little bit. So we now have defined the forward pass, backward pass, and we define the computations, how we transpose weights. So let's put it into into one figure, okay? And now let's first use a single input point. All the X are in lowercase. So I use the green color to indicate the forward pass. In the forward pass, it's quite straightforward. It's just the linear combinations. W1 times X plus B, that is how we compute Z. And then we'll compute A by applying an activation function for that applies to all layers. Okay. And then after we have the outputs, then we will need to compute the dz, dw, and db for each layer. Okay. And these gradients from dz will flow back to the previous layer. We can compute the dz's for the previous layer, the dw and db's for the previous layer as well, simply from the dz of the current layer. Okay. So that's one single example. But we know when we have multiple examples, like we have m examples in a training set or in one mini batch, then we need to vectorize everything, right? So if we want to compute the dw, we basically need to compute the dw for each single training example and sum up all the dw's and divide it by m, right? That is how we compute the mean dw's from m examples. And for db, we also do the same thing. That's the and in the forward step, we know that this part doesn't change, okay? But we need to stack the input into columns so that we have a matrix presentation or matrix representation for the x, okay? So we now write the z's and a's into capitalized variables, okay? So they are all capitalized matrices, okay? So the shape of z is also m columns, okay? But the number of rows is decided by the number of units in that layer. And the shape of A1 is the same as the shape of Z1. It has all m examples and has the same number of units in that layer, okay? That's a straightforward computation in the forward step, okay? And it's bits, there are some tricks we need to take here in a backward, in a backprop step. So for a single example, we know that it doesn't change, okay? So we have this in the previous slide. But when we have m examples, first, the a's and y's, they all become capitalized matrices and long vectors, okay? So A1, A2, the subtraction between A2 and Y is the result for DZ2, okay? And the W, the gradients for W is DZ2 times A1 transposed. And we need to divide it by M because we need to compute the mean gradients from all the examples, from all the data points, okay? And we will see that this dz2 is, in this case, it's 1 by m. It has m columns, okay? And if we times dz2 with a1 transposed, and a1 transposed is a m by 4 vector, okay? So if we times a 1 by m vector with a m by 4, the result will be a 1 by 4 matrix, okay? Which is the, or a 1 by 4 vector. And each component in that 1 by 4 vector is a very long summation over n examples, okay? So that's why we need to normalize that by the number of elements, m. And similarly, we need to apply a 1 over m for the db, okay? And we know that dz, it has, so in this case, dz has just one row. But if z have multiple rows, we need to apply a row summation. We need to compute the summation for each row individually because db is the same shape as dz, okay? We need to keep the rows. So apply that dz further backwards, we can compute the z in the previous layer, okay, by applying the the principle of backprop, okay, and the w1 also needs to be normalized by at 1/n, and db1 also needs to be normalized, okay. So that's a bit, little bit difference in when we have multiple m examples. We need to consider this m quantity, but the general principle of w transpose w2 times dz2 and the transpose of the A1 doesn't change. This is the same principles of backprop algorithms. So that's something for the M training examples. Okay. So anyway, this is something that we mentioned before. If you forgot how to compute the if you forgot the form of the backprop algorithm, you can use dimensions to check whether it's a valid computation or not. Okay, because when you multiply two matrices together, the matching matrices in the middle, they are gone. Okay, no matter how many examples you have put into a mini match, the matrix multiplication will eliminate these dimensions. Okay, and particularly for NumPy implementation, it provides so we know that we already used the np.sum function before, right? And because now we want to keep the rows, we can specify the axis argument to be 1, because the axis starts from 0 to 1 to higher dimensions. If we specify the axis to be 1, it will reduce the axis, reduce the dimension, or reduce the axis of 1, which is reduce the columns. So all the columns will be shrinked together. So, and we need to keep dimensions because we want to keep that one column as the result. So this is just a technical issue when we implement this in NumPy. Okay. And similarly for the previous layer. Okay. So if we recap this a bit, it's not very different from the case of one data points example. We now simply put a capitalized X into the input parts, and the forward pass is the exactly form as the almost the same form as the previous one, and the backward step is a bit different. Only in these parts we have 1/m here. We have 1/m here, 1/m here, right? And the dB needs to compute it as a row summation, and it is indicated by this axis equals 1 in NumPy. Okay, so that's for the vectorized version of backward propagation. All right, so everything so far are pretty, I would say, very, it's presented in a very from the scratch style. Okay, because we represent the parameters using matrices, represent the parameters, the biases as a vector, the data as a matrix or vector. So we didn't utilize the programming frameworks at all. But in practices, nowadays we don't implement neural networks manually from scratch. But that doesn't mean that the underlying mechanisms are not important. So in order to understand why the neural network can be trained, neural network models can be trained, it's very critical to understand the backpropagation algorithms. So, but in practice, we don't need to implement these ourselves. If we pick up a framework like PyTorch or TensorFlow or other frameworks, we can easily implement or train a neural network model without writing the backward step. So here I showed a example. It's a very typical neural network model example in PyTorch. Okay, so it's a model that's used for image classification. And now in this slide, we only focus on the part in the red, within the red rectangle, because in the previous part, in the part here, we have convolutional layers, and we haven't introduced convolutional neural network yet, so we don't look at it this time. So, but if we look at the red parts, we can define a neural network pretty easily using the n.linear module or function. We can use a linear to define the first hidden layer, the parameters in the first hidden layer, and the second first layer, and the last output layer. And also we can define the activation functions within this forward function by calling the f.relu function. And the f.relu is applied to the results of the first linear, and another relu applied to the second linear, and the output is directly the activation from the last hidden layer is directly used as the output. So the model definition in the red part can be described by this figure, right? So, for example, the statements and n.linear with that many input units and that many output units defines all the connections between the input layer and the output layer. Okay, and the input layer, it has that many numbers of units, and the output has 120 units. And the non-activations, the relu functions, is defined by the f.relu function. Okay, so that's the convenience of frameworks provided for the forward step. But even more conveniently, we don't need to compute the backward step at all. We need to simply call some statements, but we don't need to use the matrix multiplications to do that. For example, after we have instantiate an object from that net class, we have the object for the network. So we can do the forward pass by applying some input to the network. We have the output. Okay, so that's the output of the network, and we compared the outputs with some target variables. So this target variable is the label. Okay, and the comparison can be done by some criterion functions. Okay, so here the code is not complete, but it's basically to showcase how easy it is to use PyTorch to help you implement the backpropagation. Okay, so if we look at how we compute the loss function, here I didn't include the loss, but the loss objects or the loss variable is something you can call the backward function call that backward function will result in the values of gradients being computed. Okay, so if you look at the gradient function in loss, it has connections automatically made for you. For example, the first gradient's function is MSE loss, mean square error loss, and the second is the linear layer, and the next previous function is a ReLU layer. So everything in the computation graph is automatically constructed and defined for you if you use PyTorch in this way. Okay. All right, so that's for PyTorch. And lastly, I'd like to mention we'd like to cover the part for initialization. And we need to initialize all the parameters carefully, because if we choose like 0 for all the parameters, which means, for example, in this case, W1 is all zeros, then all the A's, they are equal. And all the gradients are all the same. So that means we don't update anything at all. Okay, all the parameters are all the same. And it doesn't make sense to have a network that have all the parameters to have the same value, because it's not picking up any distinctive patterns in the data at all. Okay, so we want to avoid this basically by randomly initializing all the weights parameters. So in NumPy, we can call the random, and use the random module to give some random numbers obtained, like extracts or obtained from a normal distribution, multiply some by some very small constants, because we don't want the parameters to be too big. Okay, and that's basically because if the parameters are too big, then the models. So first of all, the parameters that are too big are a bad model, because it could be an overfitting issue, right? But so as a result, or as something that we want to avoid, we should initialize it to relatively smaller values. Okay. And lastly, here's our last slide. A few tips for implementing neural net models, especially backprop in NumPy. We can commonly use the to check the dimensions for the matrix multiplications, and we need to pay attention to the element-wise versus vector operations. Like the dot production is applied to two vectors, but the star, the multiply, is applied to element-wise to each element of a vector. Okay, and the d of something is the partial derivative of the loss with respect to that variable. Okay, so that's all we have for the backpropagation parts. So beginning from the next lecture, we're gonna talk about using the forward pass and backward pass procedures or processes we defined so far to build a deep neural network, okay, which is not just a shallow neural networks, but deep neural networks. Okay, and after that, we will enter the convolutional neural network steps for processing image data. Okay, so that's it for the lecture today. And thank you for coming to the classroom. If you have questions, you can ask it right now. Some intuition as why the variables are called A. So let me go to the slide that has both names shown. So the A is for activation, and the z's are the inputs for the nonlinear activation, and I believe the reason for using z could be that because initially people would use sigmoid function or tanh function for the activation functions. So A is for activation, and Z is the input to the activation. Okay, and for the activation function, usually it's defined with the input variable Z. Okay, because when people define the sigmoid, it's defined upon Z. So that's why we use Z to indicate that intermediate variable or intermediate results of computation. I guess that's where the names come from. Yes, you're welcome. And if there are no questions, I will end the Zoom meeting now, and I will release the video, publish the video, and release some quiz questions about the backprop. And we are all done with backprop, but we will use it very frequently in the future. We actually don't. We must rely on backprop to update parameters in a model. All right. See you guys, and have a rest of the day. Have a good rest of the day. Bye.